All right, so welcome to the sixth video on this whole module on dimensional analysis. So this video is going to talk about unitlessness. So when exactly are you unitless with a number? And when must you be unitless in a function? There are some functions that the numbers you put into them always have to have no units. So to start off with, what is unitlessness? And it just pretty much means what it sounds like. You have no units for your number. You just have a number. So there are 4 different scenarios where that sort of thing can happen. The first is that the number just physically doesn't mean anything, right? This is the case when you do like generic math problems and they ask you, what's 5 plus 10? And you tell them 15. Well, there's no units on 15. And it's because 15 doesn't actually mean anything in the real world, right? It's just some number. So that will sometimes pop up, but it doesn't pop up too often in physics and chemistry. A lot more common one you'll see in physics and chemistry is that something doesn't have a unit because it represents a count. And that's kind of hard to explain, so I'll just do an example real quick. So let's say that you want to put up 25 meters of fencing around your house, right? And you know that the fence units are 5 meters long. How many units do you need? So how many units do you need, right? Well, okay. I need 25 meters of fencing, and they're all 5 meters long. So I'm just dividing 25 by 5. Well, okay, these both have units of meters. So those end up canceling. And I'm left with 5, right? But that doesn't have any units with it. So what does this 5 mean? Well, it's just a count of how many things we have, right? So I'm trying to figure out, I should have specified this as how many units of fencing. I'm trying to figure out how many pieces of these fencing units I need. And when I multiplied it out, I just got 5. So this really just tells me I need 5 fence units. But oftentimes, if it's just a number describing you how many things you have, you don't actually put the units with it. You would just say the number. Another reason that you could see no units in your number is that it's a result of a ratio. So let's say I'm driving a car at 60 miles per hour, and I see you're driving at, let's say, 20 miles per hour, right? How much faster am I going? How much faster am I going? Well, okay, that's just a ratio, right? So I have 60 miles per 1 hour divided by 20 miles per 1 hour. Invoking some fraction rules, this just becomes flipped. So now I have 1 hour up top here and 20 miles. Okay, hour cancels, miles cancel. I look at the numbers, I get 3 and no units, right? And that's just because every time I take a ratio, if I'm taking a ratio between 2 things, they have to have the same units to begin with. Otherwise, like, what am I comparing, right? If I'm comparing apples to oranges, that doesn't matter too much to me. I need to compare them to the same exact units. So that's why we end up unitless. And this number really is just sort of like a multiplication factor, or sometimes called a scalar, where it just tells you something is 3 times bigger, 3 times smaller, that sort of thing. So anytime, once again, that you take ratios, you're not going to have any units. The last case for having no units is sort of odd. It's definitely the weirdest one, but you'll see it. The last case of being unitless is when the unit is omitted on purpose. And that's usually because the unit is really weird and is not conventional to put in a scientific answer. So for example, let's say, I'm sitting here and there's a river that I'm looking at, right? And I see that there's fish going down the river. I don't know how to draw fish. Okay, so there's fish going down the river. Oh, these look a little bit more like nukes than fish, but they are fish. Okay, So let's say I'm sitting and looking at a river and I'm counting the fish that go by in 1 hour, right? So let's say that I see 60 fish go by in 3 hours. So I want to know what's the rate that I'm seeing fish, right? Well, okay. A rate is something per unit time. So I know that I would have to do 60 fish over 3 hours because I need that unit of time of hours in the denominator. So I would get 20 fish per hour. Well, okay. Fish per hour is not something you'd often see in science. And usually because like these things are so weird and you wouldn't ever really publish something that has units of fish per hour, they oftentimes just don't write fish. They'll write 20 over hour, or they'll do 20 and then sometimes you'll see this, which is called the inverse hour, which just means per hour. So yes, once again, if your unit is weird and not something you would conventionally see in science, they'll get rid of it. So you know the same thing happens for if you have sheep per minute or joules per hamburger and so on. A time you'll see this a lot in physics using a more normal example is if you're describing how fast something is spinning around you. Usually you would say something like, oh, it's going 20 revolutions per, let's say, per second, where a revolution is just something spinning one whole time around you. The answer you usually see in physics is actually just 20 inverse seconds. They wouldn't write revolutions because revolutions is kind of a weird unit that's not actually, I mean, it has meaning, but we don't need that. We just need this whole rate thing. All right. So the last part I wanted to touch on was a general reminder about some really common functions that have to have unitless numbers go into them. And so what I mean is stuff like log of x or e to the x or all the trigonometric functions, right? So for example, cosine, sine, and tangent. Whatever this x is in here, x must be unitless. And the reason for that is just because physically in the real world, the units of the answers wouldn't make any sense if x was not unitless. So, you know, if I take log of some distance and I had 30 meters, what does a unit of log meters mean? You know, that doesn't have any physical meaning in the real world. What does a cosine of a second mean? I don't know. It doesn't mean anything. So this can actually help you out in a lot of problems because if you know something's going wrong, if you start taking the log or the cosine of something that still has units, there's some conversion factor you still haven't done yet. And that can a lot of times tell you to go back through your answer somewhere there's something that went wrong. Just as a note to sort of protect myself if this going wrong, sometimes in chemistry and physics, like very theoretical chemistry and physics, you do have units of log something. Like usually it's something called the log of absorbance in chemistry. Those are very rare scenarios that don't usually happen. It's not too common. So I would say for the most part, any sort of number you put into these functions specifically, they must be unitless. All right, so that covers this whole video on the idea of being unitless. In the next video, we're going to talk about what the parts in a complex unit can tell you. So if I look at the units of something really complex, what can that help me understand how what that actually means in the real world?